All right. How many of you have heard of Tabby star KIC? I'm not even going to 8462852. I think. Okay. All right. Yeah. Those who read Sky and Telescope readers, Space.com readers, people like that. Okay. I am going. And those of you who don't, okay, I'm calling this the most mysterious star in the galaxy. I have a confession to make. I drew you all in with science fiction, but what I'm going to share with you tonight is, well, science. You know. But I think this is a crowd that kind of likes science, you know. You'll see what I mean as the talk goes on. And so a little apology, and I'll renew my apology when we get to the end. But it's good stuff. What I want to show you is kind of how science works in a study like this as we go through it, and hopefully we'll have some fun. I've got a demo if it works, and we'll see what happens. This, instead of trying to, we're not there yet. I'll tell you about the paper, okay? First of all, published in Astrophysical Journal back in January. There really hasn't been, I don't think there's been another paper on this yet. There are some forthcoming papers on this star, but not yet. Tabitha S. Boyajian, I'm pretty sure that's the correct pronunciation, okay, is the principal investigator, along with yours truly and 200 or so co-authors, including 28 members of the AAVSO, most of whom have far better equipment than I do. And these are amateur astronomers, like many, if not most, of you. And that's my soapbox. Okay, every large city. I'm going to call this a large city astronomy club. Probably has at least one or two AAVSO members who are rather evangelical about the organization and getting you involved in variable stars, and I'm one of those. So I apologize in advance for that. Okay. Okay, but first I'm going to cede, if this were the well of the Senate, I would be passing my time to our principal investigator, Dr. Boyajian. I think she can give you the background for those to refresh your memory if you've already read about it, and to get you started if you haven't. Uh-oh, that wasn't it. Okay. That's the laser. Okay. Oop. I'm going to have to do it with the mouse. Yeah. That's right, because it's a link. Yeah. Okay. We got to watch a commercial. Okay. There we go. Whoop. Hope everybody can hear that.
Extraordinary claims require extraordinary evidence. And it is my job, my responsibility as an astronomer to remind people that alien hypotheses should always be a last resort. Now, I want to tell you a story about that. It involves data from a NASA mission, ordinary people, and one of the most extraordinary stars in our galaxy. It began in 2009 with the launch of NASA's Kepler mission. Kepler's main scientific objective was to find planets outside of our solar system. It did this by staring at a single field in the sky, this one with all the tiny boxes. And in this one field, it monitored the brightness of over 150,000 stars continuously for 4 years, taking a data point every 30 minutes. It was looking for what astronomers call a transit. This is when the planet's orbit is aligned in our line of sight, just so that the planet crosses in front of a star. And when this happens, it blocks out a tiny bit of starlight, which you can see as a dip in this curve. And so the team at NASA had developed very sophisticated computers to search for transits in all the Kepler data. At the same time of the first data release, astronomers at Yale were wondering an interesting thing. What if computers miss something? And so we launched the citizen science project called Planet Hunters to have people look at the same data. The human brain has an amazing ability for pattern recognition, sometimes even better than a computer. However, there was a lot of skepticism around this. my colleague Deborah Fisher, founder of the Planet Hunters Project, said that people at the time were saying, "You're crazy. There's no way that a computer will miss a signal." And so it was on, the classic human versus machine gamble. And if we found one planet, we would be thrilled. When I joined the team 4 years ago, we had already found a couple. And today, with the help of over 300,000 science enthusiasts, we have found dozens. And we've also found one of the most mysterious stars in our galaxy. So to understand this, let me show you what a normal transit in Kepler data looks like. On this graph, on the left-hand side, you have the amount of light, and on the bottom is time. The white line is the light just from the star, what astronomers call a light curve. Now, when a planet transits the star, it blocks out a little bit of this light, and the depth of this transit reflects the size of the object itself. And so, for example, let's take Jupiter. Planets don't get much bigger than Jupiter. Jupiter will make a 1% drop in a star's brightness. Earth, on the other hand, is 11 times smaller than Jupiter, and signal is barely visible in the data. So back to our mystery. A few years ago, planet hunters were sifting through data looking for transits, and they spotted a mysterious signal coming from the star KIC 8462852. The observations in May of 2009 were the first they spotted, and they started talking about this in discussion forums. They said an object like Jupiter will make a drop like this in the star's light, but they're also saying it was giant. You see, transits normally only last for a few hours, and this one lasted for almost a week. They were also saying that it looks asymmetric, meaning that instead of the clean U-shaped dip that we saw with Jupiter, it had this strange slope that you can see on the left side. This seemed to indicate that whatever is getting in the way and blocking the starlight was not circular like a planet. There are a few more dips that happened, but for a couple of years, it was pretty quiet. And then, in March of 2011, we see this. The star's light drops by a whole 15%. And this is huge compared to a planet, which would only make a 1% drop. We describe this feature as both smooth and clean. It also is asymmetric, having a gradual dimming that lasts almost a week, and then it snaps right back up to normal in just a matter of days. And again, after this, not much happens. Until February of 2013, things start to get really crazy. There is a huge complex of dips in the light curve that appear, and they last for like 100 days, all the way up into the Kepler mission's end. These dips have variable shapes. Some are very sharp and some are broad, and they also have variable durations. Some last just for a day or two, and some for more than a week. And there's also up and down trends within some of these dips, almost like several independent events were superimposed on top of each other. And at this time, the star drops in its brightness over 20%. This means that whatever is blocking its light has an area of over 1,000 times the area of our planet Earth. This is truly remarkable. And so the citizen scientists, when they saw this, they notified the science team that they found something weird enough that it might be worth following up. And so when the science team looked at it, we're like, yeah, there's probably just something wrong with the data. But we looked really, really, really hard, and the data were good. And so what was happening had to be astrophysical, meaning that something in space was getting in the way and blocking starlight. And so at this point, we set out to learn everything we could about the star to see if we could find any clues to what was going on. And the citizen scientists who helped us with this discovery, they joined along for the ride, watching science in action firsthand. First, somebody said, well, you know, what if this star was actually very young and it still had the cloud of material it was born from surrounding it? And then somebody else said, well, what if the star had already formed planets and two of these planets had collided, similar to the Earth-Moon forming event? Well, both of these theories could explain part of the data, but the difficulties were that the star showed no signs of being young, and there was no glow from any of the material that was heated up by the star's light. And you would expect this if the star was young or if there was a collision and a lot of dust was produced. And so somebody else said, well, how about a huge swarm of comets that are passing by the star in a very elliptical orbit? Well, it ends up that this is actually consistent with our observations. But I agree, it does feel a little contrived. You see, it would take hundreds of comets to reproduce what we're observing. And these are only the comets that happen to pass between us and the star. And so, in reality, we're talking thousands to tens of thousands of comets. But of all the bad ideas we had, this one was the best. And so we went ahead and published our findings. Now let me tell you, this was one of the hardest papers I ever wrote. Scientists are meant to publish results, and this situation was far from that. And so we decided to give it a catchy title. We called it Where's the Flux? I will let you work out the acronym. So this isn't the end of the story. Around the same time I was writing this paper, I met with a colleague of mine, Jason Wright, and he was also writing a paper on Kepler Data. And he was saying that with Kepler's extreme precision, it could actually detect alien megastructures around stars. But it didn't. And then I showed him this weird data that our citizen scientists had found. And he said to me, ah, crap, Tabby, now I have to rewrite my paper. So yes, the natural explanations were weak. And we were curious now. So we had to find a way to rule out aliens. So together, we convinced a colleague of ours who works on SETI, the Search for Extraterrestrial Intelligence, that this would be an extraordinary target to pursue. We wrote a proposal to observe the star with the world's largest radio telescope at the Green Bank Observatory. A couple months later, news of this proposal got leaked to the press. And now there are thousands of articles, over 10,000 articles on this star alone. And if you search Google Images, this is what you'll find. Now you may be wondering, okay, Tabby, well, how do aliens actually explain this light curve? Okay, well, imagine a civilization that's much more advanced than our own. In this hypothetical circumstance, the civilization would have exhausted the energy supply of their home planet. So where could they get more energy? Well, they have a host star, just like we have a sun. And so if they were able to capture more energy from this star, then that would solve their energy needs. So they would go and build huge structures. These giant megastructures, like ginormous solar panels, are called Dyson spheres. This image above are lots of artist impressions of Dyson spheres. It's really hard to provide perspective on the vastness of these things. But you can think of it this way. The Earth-Moon distance is 250,000 miles. The simplest element on one of these structures is 100 times that size. They're enormous. And now imagine one of these structures in motion around the star. You can see how it would produce anomalies in the data, such as uneven, unnatural-looking dips. But it remains that even alien megastructures cannot defy the laws of physics. You see, anything that uses a lot of energy is going to produce heat. And we don't observe this. But it could be something as simple as they're just rewriting it away in another direction, just not at Earth. Another idea that's one of my personal favorites is that we had just witnessed an interplanetary space battle and the catastrophic destruction
That's not a
of the
moon.
planet. Now I admit that this would produce a lot of dust that we don't observe, but if we're already invoking aliens in this explanation, then who's to say they didn't efficiently clean up all this mess for recycling purposes? You can see how this quickly captures your imagination. Well, there you have it. We're in a situation that could unfold to be a natural phenomenon we don't understand, or an alien technology we don't understand. Personally, as a scientist, my money is on the natural explanation. But don't get me wrong, I do think it would be awesome to find aliens. Either way, there is something new and really interesting to discover. So what happens next? We need to continue to observe the star to learn out more what's happening. But professional astronomers, like me, we have limited resources for this kind of thing. And Kepler is on to a different mission. And I'm happy to say that, once again, citizen scientists have come in and saved the day. You see, this time, amateur astronomers with their backyard telescopes stepped up immediately and started observing the star nightly at their own facilities. And I am so excited to see what they're finding. What's amazing to me is that this star would have never been found by computers because we just weren't looking for something like this. And what's more exciting is that there's more data to come. There are new missions that are coming up that are observing millions of more stars all over the sky. And just think, what will it mean when we find another star like this? And what will it mean if we don't find another star like this? Thank you.
Okay. All right, so that was, when was this submitted? Oh, 2016. So it's been a little while. More data is needed. This is exciting because even if it isn't a Dyson sphere, which, you know, wouldn't you love it? Okay. It might be a brand new class of variable stars, which should get anybody interested in astronomy interested, especially somebody like me who loves variable stars so much. So, because I've read the wonderful stories of the discovery of new variable stars, and we're getting to witness this in our lifetime. So it's kind of nice. So to review, the dips were recorded by the Kepler instruments. One of the things that I did not get was a picture of the Kepler satellite. I'm sorry about that. Most of you have heard of Kepler. Let's see a show of hands real quick. Yeah. It's a space telescope. The Hubble, no, is not the only space telescope, in case you're wondering. Lots of them are up there, and I'm going to mention several more because several other space telescopes were used in gathering more data. Software missed the dips, remember? Software couldn't do it, but people could. To May 2009, they were flagged. The dimmings are more than 10 times those expected during a planetary transit of a Jupiter-like object, remember that? And in one case, 22 times. The light curves don't look like those of a transiting planet, remember that? Because they're just not deep enough, okay? And so what were the causes? Well, star spots. Star spots, don't you mean sunspots? No, I mean star spots. Our sun can't be the only star in the universe with spots, can it? And it isn't. Let me show you a picture of another star in the constellation of Serpens, which has spots. See that? Variations in its surface brightness. This was, and you're like, what? That can't be a real image. You mean technology has reached the point where we can image stars several tens of light years away and image their surfaces? Yes. Actually, using a technique called interferometry. You can read about that. I'm going to be moving pretty quickly. Lacing together mathematically the results of several optical telescopes, this image was made of the red supergiant star Pi 1 Gruis, which implies it's in a different constellation. I'm not sure why. What the information I had said that it was in Serpens. I've never observed it myself. I think it's too far south, actually. Oh, you can? Oh. What is it, declination, do you know? Oh, okay. So low but not impossible, right. Okay, cool. One of the other proposals was circumstellar material. Here's an artist rendering. So basically, when unusually distributed clumps of gas get in front of the star in our line of sight, it could cause these unusual dips. That was one of the proposed solutions. Changes in the interstellar medium, and of course, I'm going to find the most interesting part of the interstellar medium I possibly can, the pillars of creation, which I think everybody in this room has probably seen at least once. So I got a quick quiz for y'all. Okay, which star is brighter? This one or this one. You see that little star you can barely see inside the nebulosity there? Anybody want to venture an answer? Yeah, that would be wise not to venture an answer. You know why? Because we need a lot more information to tell, okay? Yeah. As a matter of fact, the effect of dust in particular on, and also gas, but mainly dust, on the extinction of light as it gets to Earth was first studied in the early part of the 20th century. Yeah, I believe that's right. And was accounted for. And so certain stars that were thought to be further away actually were understood to be a lot closer when reddening was taken into account. We may get to talk about that later. Dust clouds associated with orbiting planets. I don't have a graphic for this, but planets are gravitating bodies. If something else is going on in the vicinity of the star that's producing a lot of dust, these planets might attract it, form a cloud, and carry it around with them. Okay? You would expect some sort of periodicity, and there's possibly that in the data. We may get to that. Exocomets, I decided to let that fly in, of course. You see what I did there? Okay. Anyway, exocomets, of course, they don't fly any more or less than planets. They just have to be in more eccentric orbits. And she mentioned the swarms of hundreds or thousands of comets that might explain the dips in the brightness. A ringed planet, okay, and so kind of like PDS 110 in Orion, okay, as this planet, which orbits apparently this star with a lot of nebulosity around it, I'm not sure why that's the case, but as this star orbits, if its orbital inclination and the inclination of the rings is just right, the starlight might filter through the rings one by one, or the ring systems, and you might get unusual light curves out of that, okay? Think Super Saturn, okay? And there is one in Orion, and there was an observing campaign with the AVSO for people, again, with better equipment than I have. I'm a visual observer. Trojan asteroid swarms, okay? All right, Lagrange points. Some of you know what those are. They're balance points of gravity. So L1 is the easiest to understand. This is the point at which solar and Earth's gravity exactly cancel out. There are others in different vicinities. Trojan asteroids tend to accumulate, not for Earth, I think there may be a few, but not many, but for more massive planets like Jupiter and Saturn. Okay, so there are a lot of Trojan asteroids in the outer regions of our solar system, and if there are enough of them, who knows, and they collide often enough, they might produce enough dust to cause some of the dips in the light curve. Okay. Colliding planets, she had a great graphic on that, so I'm not going to, I can't improve on hers. And, of course, everybody's favorite, come on, admit it. We have found the first alien civilization. By the way, this star happens to be, I don't want to forget, 1,500 light years away. So, and as we're going to see, whatever was happening is still happening. And so, what is that? Secular dimming. This is not as opposed to religious dimming, okay? Well, I won't argue about periods of history, but anyway, okay. So whatever, you can insert your own ideas there. Secular dimming means long-term dimming, okay? Global, so to speak, dimming, okay? So a study in 2016, not long after the study that Dr. Boyajian was reporting, showed that it's based on the Harvard plates, okay, which are now being digitized in a program called the DASH program, a 16% decline in brightness, relatively steady over the past century. Harvard plates have been going strong with a couple of gaps in the 40s, since the 1890s. A second study cast doubt by suggesting systematic error in the DASH source plates or analysis. But a third study reported 3% dimming from 2000 to 2013 in the Kepler images themselves. So an independent confirmation, and then further confirmation from, here are those other space telescopes. This is a ground-based, but Spitzer and Swift are space telescopes, multi-band, multicolor. The dimming occurs in multiple bands, okay? So it's, in other words, it's real, okay? So, in short, the brightness variations occur over multiple time scales from days to maybe even centuries. This paper was about reporting the observations since Kepler from professionals and amateurs The amateur data is in there. I didn't get to show you. I mean, I looked at putting AAVSO light curves in there. It was harder to see the results in the light curves without analysis, so I started doing the analysis and ran out of time. So, yeah. Anyway. Okay, so the campaign was announced in May, but there was a previous campaign that had been announced in 2015, and I did a few observations at that time and did some more in 2017 in the summer. So the dips have names. They were named by people who coughed up the money. The Kickstarter funders of some of the ground-based telescopes naturally get to name the dips. And there are 4 of them, and we'll get to that. Okay. Okay, there are 4 lines of evidence considered by this paper. And only one of them shows positive results. What are negative results? When you have a hypothesis, you're going to see something, and you look, and it ain't there. Okay? Yeah. But it's important to not see things, because it can rule things out. It can constrain hypotheses, and it can lead you in the right direction by a series of blind alleys. Remember what she said, when everything else is eliminated, right? Even if you have an unlikely solution, it's got to be right, you know, or it's more likely to be right. You've got to be careful there. Spectroscopy, yeah, process of elimination, works in science, tells us about the composition. I'm not sure what I meant by location of the blocking material, anyway. But I do know what I meant by composition. One of the primary uses of spectroscopy is to identify what's out there, okay? Both elements and compounds. We'll talk a little bit about that. Sometimes can reveal the presence of an orbiting companion by, these are called spectroscopic binaries, and the first person to notice from the spectrum of light, because of something called Doppler shift, the presence of a binary star system for which the pair could not be resolved, was Antonia Maury, who was one of the Harvard computers, female computers, astronomers that worked at Harvard College Observatory. And since then, this is just a normal tool in the toolkit of professional astronomers. Okay? In addition to spectroscopy, we have polarimetry, polarized light. And at this point, I think I'm supposed to hand out polarized glasses that I bought at Walmart. Oops, I forgot. I didn't have time to get to Walmart either. But I think we've all played with, how many of you have ever had a pair of polarized? Okay, I also should have brought my polarized filter from the lab, but I couldn't find it. Haven't taught that optics in a while, you know. So what can they reveal? So polarized light, when you rotate, and we'll talk more about, if we have time, we'll talk more about this. When you rotate a polarized filter, like in the eyepiece of glasses, and you see reflected light, say off a street or something like that, the filter has the effect of blocking some of the light, because it makes the electric and magnetic fields only vibrate in a single direction, as opposed to a random set of directions. So if you can imagine a stream of photons, all with different, vibrating this way, vibrating that way, vibrating this way, they come through this filter, and they're all vibrating the same way. If we have time, we'll talk about the mechanism for that, but keep going. Oh, and my personal favorite here, Radio SETI. She talked about the Green Bank telescope, and I think a different telescope was used in this current paper. Is ET broadcasting? You know, we'll see. We'll find out. You know, are we getting signals from this star? Okay. I already talked about the Kickstarter campaign. I'm going to skip that. I'll just show you one of the alerts. This was the original alert that came out, so you know what an VSO alert kind of looks like. And it says, I think just reading the headline is enough. Observations requested for KIC 846-2852. Okay, goes into detail about what they're looking for and what kind of equipment you ought to use and that sort of thing. Okay, where were we? Oh, here we go. Okay. Oh. Okay, I'm going to have to, there we go. Oh, too far. Okay. What are the 4 dips? Okay, the first one was called ELSI, and it was detected by the Las Cumbres network starting in May 2017. As soon as that, these are really 2 telescopes, one in Hawaii and the other one, can't remember. Okay, it was confirmed in Fairborn, Tennessee. Does anybody know that? What's the other Las Cumbres telescope? Anyway, there are 2 of them, 2 professional observatories. Later confirmed not only in Tennessee, at Tennessee State, but also 8 additional professional observatories, okay, worldwide. She mentioned the asymmetric nature, the non-mirror-like nature of the dips, the non-U shape. Okay, they tend to be deeper initially and then recover slowly. Okay, these were also confirmed by VSO observers, and they're in the data. Although she doesn't directly cite the data, which is a little bit disappointing. Yes. Okay.
The 28-inch telescope at Rainwater Observatory is also on the Los Cumbres network.
Oh, okay. Huh.
The guy that started all that is the one that paid for rebuilding the telescope.
Okay. Interesting. Yeah, she only mentioned 2, maybe a 3rd telescope, but there are probably more in the network than.
2-meter class, I think 3 or 4 1-meter class telescopes, and then a whole series of smaller.
And the ones that were mentioned were 0.4 meter, I think, if I remember right. So that's, yeah, okay, cool. So there are a lot more quite a few in there. Okay, this is the photometry, and these are the 3 observatories involved. ELP is somewhere in Texas. I have no idea. Okay. OCG, I think, is the Keck telescope, and TFN, I think, is in the Canary Islands, but I'm not sure. Okay. Anyway, LC, as you can see, sudden drop-off in brightness to the tune of nearly 2%. So if you look at this, read this as 100%. Okay. Read that as 98%, read that as 96%. When you look at this, you're nearly at 2%. The deepest one was the last one, Angkor, over here. We're going to get to that one. Celeste is also asymmetric. Now, it may look a little bit less that way, but if you take a look, it comes up and it begins to recover a little bit, and then it kind of slopes up here. And so it's still asymmetric. This is, I wish they'd fit a nice little line to it so you can see that, but it's kind of nice. Also, notice, for about a month, it stayed low, about 0.5% under normal. So the dotted line here is the normal brightness of the star. Okay, and then Skara Brae is the most U-shaped, I guess you could say normal-looking, I guess curve that you're going to see here. Angkor is the deepest, goes down to a little bit over 2%. And then it brightens, interestingly enough. It actually gets brighter than the average. And then it begins to settle back down toward the end of the 300 and some days. Okay, these are Julian dates. I won't go into that right now unless somebody asks. But okay, and this comes from the paper. This is one of the tables. Okay, this curve we're going to come back to. This curve represents the only positive result in the study. So I'll just tell you what everything is here. B is for blue, right? Okay, not hard to figure. The yellow is red light, somewhere between 600 and 700 nanometers, I guess, toward the red end of visible light that the human eye can detect. And then the red line there is infrared. Okay. We'll come back to this graph later. What does it mean? How come the curves don't lie on top of one another? Talk about that soon. Oh, the spectrum tubes. Yeah. I did bring something from my lab, and I've got about 10 of them. So let's see. So 1, 2, 3, 4, 5, 6. Yeah, about 2 or 3 per row here. Pass them around. There we go. And gosh, most of the light sources are blocked. But if you can look at any light in the room, look through the end with a slit. Okay, the other end is a diffraction grating. These should be properly oriented, and if you look just slightly off to the left or the right at a bright source, you're going to see a rainbow effect or a spectrum. And I'm running out of these, but I'll put them up here, and one for this table, and you can look around. And yeah, there we go. That helps. All right. Yeah. Okay. So what you are doing is you're going to look at, if you look at different light sources, you're doing a sort of spectrum analysis. You're looking to see if there are differences or similarities in these light sources. And this is essentially what astronomers do with the light from distant stars. Yeah. Looking at the time here. Yeah, okay. So I don't know give you some time to do that. Yeah, there we go. I don't know what the...
But this is an LED.
yeah, it's going to be narrow band, so... Or you can look at your cell phone if you have a flashlight in your cell phone, which is probably also LED, you know. Yeah. So get a chance to look at that. I've already mentioned how spectra are used in astronomy. They're used to detect motion as well from the Doppler effect. And we're going to do a crash course in spectroscopy, hopefully lasting no more than 5 to 6 minutes. Okay, so this is the fastest course in spectroscopy you'll ever have, you know. Yeah, Rick's looking at me like you're crazy. Yeah, I know. Okay. NEO-wise, the IR results are still kind of coming in. They did actually, as I looked at the paper again, I was like, oh, they do have some results. But they weren't the most important thing reported. Reported in the abstract or in the conclusions, really. Okay. Everybody knows what this is. How many of you have had something like this at home in your room, maybe growing up, and it split the light up? This is the other way, common way to break light into its constituent colors, prism instead of a diffraction grating. And this depends upon the fact that the light disperses because the index of refraction, or the way that the light is bent by the glass, changes with the wavelength. And so red light, and this affects the speed of light. Okay, blue light travels slower than red light in a refractive or bending medium. Okay, so that's just, and this goes back to good old Isaac Newton. I thought somebody was going to say John Mitchell, but Newton lived before Mitchell, so you know, Michel, I mispronounced his name again. Okay, yeah. So I wonder what he didn't do, right? Okay. Here very quickly in our crash course is the visible spectrum. And I like to say it this way, although it's maybe a little bit technically imprecise, but I don't care about that, okay? The light that we all can see with the human eye is only the tiniest infinitesimal fraction of all the light that is out there, okay? A light is an electromagnetic wave. It is have a vibrating magnetic part that goes one way and a vibrating electric field that goes the other way, okay? Talking about polarized light earlier, and you can see that we go all the way from gamma rays and X-rays, which are high energy, you know, gamma rays from nuclear experiments and atomic bombs and other astrophysical sources. X-rays, go to the dentist, you know, and so on. A nice technique for looking inside your body. Ultraviolet, put on that sunblock, right? Okay. UV, the visible range from violet to red, and then beyond red, night vision goggles. There's an application. Microwave, yes, your microwave at home, okay. Which, by the way, has polarizing filters to block the intensity so that your pacemaker doesn't get messed up by the microwave radiation. And radio waves, right? Don't need to elaborate on that. Okay. There's the spectrum. So all of this stuff is the same stuff, is my point. We tend to think about it. How many of you in your daily life, even if you kind of know better, how many of you tend to think of these as very different things? We've heard of them all, but it's all the same thing. Notice, it's just a gradual variation in the wavelength and frequency from left to right. Oh, and I need to point out, short wavelength means high frequency and high energy. So this is the high energy end. This is the lower energy end. Okay, blue is more energetic than red light. I love this. This is a free Wikimedia Commons animated GIF. I couldn't believe it. You know, and somebody named Lucas Barbarossa produced this wonderful thing, and it actually shows the relative speeds. If you look at it carefully, you can see that I thought I could see the red light outpacing the blue. It does, yeah. You know, and so this is a beautiful image of what we were talking about there. So just thought I would let you take a look at that real quick. Yeah, the violet's definitely going slower. Okay. Okay, so there are three types of spectra. Some of you already know about this. Continuous, if you take your spectrum tube and you were to look at sunlight, not directly, I have to say this every single time, 6 times, never don't point anything at the sun, really, except for a telescope with a proper filter. Anyway, you look at properly reflected sunlight on a white surface, you're going to see this, almost. Unless you have keen eyes or a good spectroscope, you're going to more or less see this. Okay, we'll get to that in a minute. What will you see if you have a better spectroscope? That's coming up. Then we have an emission spectrum in which only certain colors are shown. Remember, the color relates to the frequency, and the frequency to the wavelength. The formula, the only math I've given you so far, the speed of a wave is equal to its frequency times its wavelength, okay? And so the higher the frequency, the higher the energy. And so an emission spectrum, which you get actually up in these things, these fluorescent lamps, give you a somewhat of an emission spectrum. You can get specially designed tubes that contain individual gases like hydrogen and helium, and when you hook them up to an electric current, you get, and look at them through the spectroscope, you get an emission spectrum. Also, out in space, there are notable emission nebulae. I'm not going to, if I name one, I'm afraid I'm going to get it wrong. So I think one of the nebulae in Orion is an emission nebula. And so what happens is you have hot young stars or hot stars exciting nearby gas, which then is excited in the electrons decay. We're gonna see that later, to lower energy states, and they emit light of certain colors. And this also, each chemical element has its own unique spectrum. And so this was the way that astronomers first identified helium. Helium was discovered in space. It wasn't discovered on Earth. It was discovered in the photosphere of the sun, in the sun's atmosphere, actually. And then later it was discovered on Earth, isolated on Earth. Okay, so if you really look hard at the sun's spectrum, you will see an absorption spectrum. These are called Fraunhofer lines. And they perfectly match, in this case, the emission spectrum. This must be the same chemical element, okay? I'm really not I should say that's helium, or hydrogen, but anyway, I don't know. Okay. No. Anyway, yeah, so you're looking at this, and what's happening is there's the light, full spectrum light, all white light is coming from behind whatever material is obstructing it, coming through it to you, and it's being partially absorbed at those specific colors. Okay. That's an absorption spectrum, and it's absorption spectrums that absorb a lot of time for graduate students and other people working in astronomy. Okay. Anyway, it's very absorbing. Okay. Right here we have a partial. This is a real quick explanation based on the Bohr model of the atom, which, by the way, is about 100 years out of date. But okay. But it's a good picture. Some lies are more instructive than others, and this is one of them. Okay, I'll get to that in a minute. So what we have here in an emission spectrum, like you saw earlier, is an electron which was in a higher energy state, which also further out from the nucleus of the atom. Here's the nucleus with the protons and the neutrons, and the electrons are surrounding it in different energy shells. Okay, as it spontaneously, unpredictably decays, individually, we can't predict individual decays. We can only predict them en masse, okay, because of something very deep in the nature of the world. But the electron drops and emits light. And notice, it's red light, which means low energy, right? Okay. And down here, we have blue light. Why? Because we're skipping from level 3 to level 1, and that's more energy, bigger energy gap, therefore bluer light. So you begin to see, I hope, how the spectrum tells us the structure of the atom. And from the structure of the atom, we then know what type of atom it is. And we can even detect ions, molecules, all kinds of things more complicated than simple atoms, okay, elements. Absorption spectrum is precisely the inverse of this process. This atom is sitting along with an electron in its ground state, maybe, and another electron in the next energy state above it, and along comes a red photon from some source. We don't know, maybe some sun is nearby, right? And jiggles it and gives it energy, only a precise amount of energy. Hey, there's nothing in between here. No electrons can go there. That's why quantum theory is called quantum theory, because these things have to jump steps. They can't exist in between. And when it does, and it gives it just the right amount of energy by chance, it hops up here. Same thing going on here, except it needs more energy to go up to this level. So I probably spent too long on that slide. Okay. The truth is closer to this picture. This is the ugly truth. The ugly truth is that uncertainty lurks at the base of nature, so that we cannot say, I mean, I never get used to this, okay? So what's really going on? Look at this picture right here. This, when you see the intense light, like the brightest light here tells you that you are most likely to find an electron here, and the darker it gets, the less likely it is to find an electron. These are probability clouds. It really is an ugly idea, but as Niels Bohr said when Einstein said God would never make the world that way, and Bohr responded, well, who are we to tell God how to make the world, right? It's just the way it is. I don't know why. Nobody knows why, okay? But we can use this theory. The quantum theory is very helpful in predicting things, okay? The uncertainty principle, you cannot know the velocity. There are several conjoined variables, but the one that we most talk about, you cannot know the velocity of an electron or any particle at the same time you know where it is. So the more closely you know its velocity, the less you know about its position, and vice versa, okay? And this is why we cannot pin down the electrons, kind of like soap in the shower, okay? Well, now we have the Doppler effect. Everybody knows what this is experientially. If you haven't put 2 and 2 together, I'll help you out here. Huh? What happens? Car comes by, honking the horn. Pitch goes up, pitch goes down. In front of the vehicle, the wave fronts are squashed together so that the wavelength is smaller and the energy is higher and the frequency is larger also, see? And behind the vehicle, look, the waves are further spaced apart, lower energy, lower frequency. And I've got a little picture, okay, for you. And we're going to have to get, if we start running out of time, I'll cut to the results, okay? Got a graphic here. It was really, really hard to find free stuff. So I'm just linking to this at NASA. We're giving them credit, okay? If you can look at this, remember those lines? Okay, well, let's say that there's a planet orbiting a star, and we're seeing the light from that star, okay? I think this is supposed to be, are we looking at the planet or are we looking at the star, okay? We're looking at this object, the pink object. As it moves away, the spectrum, the lines shift toward the red end, and as it moves toward us, it shifts toward the blue end. So it's the shifting of the lines that tell us the relative motion of light-emitting bodies in outer space. And by the way, Doppler radar uses some of the same principles with radio waves. We know how fast a storm is moving. A version of this was used to determine my daughter's heartbeat at age 5 weeks. Yeah, I was amazed. I didn't know they could detect it that early. They were using Doppler velocimetry or something like that with lasers. It's really, really neat. Okay, let's see. Let's close this up and back. Okay. Okay. And then, yep. Scroll down here. We've got all the way down there. I'm doing great, I thought. Okay. Okay, I hope so. Oh, yeah, that's the car. Okay. Okay, the black dots you're going to see in the next graphs are prior to the dipping event, the first dipping event, LC, and the red line is during LC. Okay. Do you see any change here? Nope. Well, what I mean is, does the red line match the black dots? Yeah, sure does. How about over here? Yeah, sure does. This is the sodium, one of the two of the sodium yellow doublet, if you've ever heard of that. This is line D1 and has a split in it. Why does it have a split in it? I can think of at least 3 explanations, and I'm not going to give any of them, okay? So I'm not sure that they're right, okay? And then over here we have a calcium line, which is found a lot in stars, their photospheres, their atmospheres. Okay, and notice that before and after the dip, the spectrum matches almost perfectly. This is a negative result. Okay, no change. Okay, no changes during the LC event for the spectral lines studied. In addition, there was no wobbling. Remember that with the Doppler effect? There was no Doppler effect down to about 400 meters per second, 900 miles an hour. That sounds like a lot, doesn't it? But it's really not. Okay, this means that we are very likely not dealing with a binary star system. Okay, that was one of the proposals. I don't know if she mentioned it, but and I think somewhere in the paper, I couldn't find it again. She mentions that this eliminates anything Jupiter size or larger. So does that mean it can't be? No, it just means that we're zeroing in on things, right? We're eliminating some of the possibilities here. So if there are planets, they're small, or there may be small gas giants. Okay, I can't hand out the polarized filters, the Walmart glasses. We talked about that. Polarized light. I'm going to go faster here. Okay, turns out that, I can just tell you this now, dust grains can act like a polarized filter in space. Okay, so because a magnetic field near a star, or maybe the magnetic field from the galaxy or from a nebula or something of that nature, because in a local region of space it aligns one way, dust grains, if they are ferromagnetic or if they're susceptible, magnetically susceptible, they can line up. Light passing through them then can become polarized. And we can measure the degree of polarization and determine the magnetic structure of space, the magnetic field in a certain region. Okay. Was that studied in this study? Yeah. Creates a polarized filter so we can reveal the shape of the magnetic field and then infer other properties of the things that are going on there. Okay. Let's see. I have a graphic down here. This is kind of neat because I can't do the demo, so here goes. I'll just show this one. This is about 30 seconds. Okay, so this is light of all different polarizations coming out of a flashlight. And then in a minute, there's going to be a polarized filter. It's going to come in the way, and looky there. It's only vibrating one way. And of course, there's also a magnetic field component vibrating this way, but the convention is to use the electric field. Okay, there it is. Does that make more sense? A little bit. Okay. All right, now I don't want to spend all my time on the... Okay. Okay. Is there any difference in polars? Okay, I got to make sure this is right. All right, yeah. HD 191098, the Henry Draper catalog. This is a nearby star. It's in the same region of space as KIC 846, as Tabby star, we'll say. I'm tired of saying that. So Tabby star versus the Czech star. This is our Czech star. Czech star in red, Tabby star in black. Do y'all see any difference? Minor, a little bit of noisy, probably just noise, right? Okay. Over here, percent polarization, very close together, the two stars, here and here. No statistically significant variation in the polarized light that we're seeing from both. What that says is that the polarization of the light in that region of space has nothing to do with either star. It has to do with the characteristics of the medium in between of whatever is out there in space. And so it has nothing to do with whatever it is that's going on with Tabby's star. Another negative result. Darn. Okay. That's okay though. No change compared to the control star during dips. Okay. Now, we finally get to the positive result. Differential photometry, and I have something to click here. Let's go back to that. I told you we would go back to that. Okay. Notice what color is the dimmest? You can see blue is the dimmest. It's 3% extinguished versus red at about 2% versus infrared a little over 1%. What does that mean? In a word, dust. Yes, ladies and gentlemen, I'm sorry to report that you came in here looking for aliens and all I've got for you is dust. Okay. Well, it's a little bit more exciting than that. Okay. So how do we know it's dust? How do we know? Well, let's go down to the picture. I'm just going to have to directly do this. Where is my graphic? Okay. All right. It turns out we have two mechanisms for this. One is called Rayleigh scattering. If you're into math, Rayleigh scattering is inversely proportional to the fourth power of the wavelength. Okay. If that doesn't sound right to you, just look at it this way. It's why the sky is blue. Okay. Because blue light is scattered a much more, about 10 times more than red light. Okay, according to this scattering mechanism. All right, the graph says it better than that's not even an equation. That's just a proportionality. So you can see percent scattered way up there. So what gets through? Red light gets through. This is why sunsets are red. Okay, yeah. I've got a graphic for that too. I got a graphic for everything. Okay. There's if we're talking. Okay, so this I didn't tell you. This occurs when the wavelength is much larger than the particles. Okay? Mie scattering occurs, discovered by Gustav Mie in I think the 19th century, occurs when the particle sizes and the wavelengths are closer together. This is a bad diagram, and so you can tell I did it. Okay, this is my diagram for Mie scattering using an online calculator, graphing calculator, and a bunch of paint paint app. Okay, this is 1 over lambda, so you can see that we have nearly 25% here, and it scatters about not as much, 15% of the red light. Okay, here it scatters very little of the red light. Okay, so you can kind of see the contrast. I tried to make the scales the same as much as I possibly could. Okay, so that's the difference. The scattering of dust that's thought to be in the vicinity of Tabby star is governed by something like me scattering. I say something like because I started to do the lit search and I got quickly in over my head. Let's just say it's a mathematical model that's derived from me scattering. Or if you just want to throw that away, say it's me scattering. So that's my story. I'm sticking to that story. Okay. Okay. These models get complicated. Okay. Now, what I have here, I want to demonstrate me scattering to you. This is sort of a partial lie, but it's still true. Okay. We tell a lot of good lies in physics and chemistry in order to get the truth out. I know that sounds bad, but it really isn't. Okay. And this is analogous to me. It's kind of like me scattering.
Bottom button.
Yeah, it's the bottom button, but it's not. Okay, maybe I'll just turn it. I don't know.
Go back to slideshow.
Okay.
Oh, that's right.
Oh, okay, got it. Yeah. Okay, cool. Okay. I have some water here, and some of you know what I'm about to do. This is coffee creamer, and there's at least one person, maybe more than one person in this room who can tell me that I'm not producing a colloidal suspension. Let me just tell you what that is. Colloidal suspensions happen when you have particles that are smaller than a bacterium, basically, and maybe larger than a virus, or maybe down to about that size. Okay, so I'm putting just a little bit in here. This is a scientific instrument. It only looks like a Wendy's Frosty spoon. Okay, and so that was. As you stir it up, there's enough ambient light in the room that some of you sitting close might see the faint blue light already. That's because, of course, blue. The basic physics is the same. Blue light is preferentially scattered. Okay. What I'm going to do now is turn on the lamp, and that's far away. Can you see the color? What color is that? Thank you. What a nice man. He said it was red. Okay. Yeah. And look at the light here. Does this look red? Whitish? Bluish? Yeah. I don't know if adding more is going to help. This is not a very carefully measured. Okay, let's try this and see if we can get it to be redder. Yeah. That's what I was originally going to do. Let's just try that right here. Yeah, there you go. See that? Blue sky, red sunset, artificial sunset. Okay. Here we are on Earth looking through whatever it is that's around Tabby star, which is right here, causing the scattering, and we're seeing red light, which means that there's less blue light, right? Which means that the blue light is depressed. Now, if I can get the screen to come down again and turn it back on, we'll take a look at that graph again, and hopefully it'll all make sense. And looking at the time here, and I'm pretty much out of it. Okay. All right. This was just in case the demo failed, and thankfully it didn't. Okay. Here's another picture. Here's the star. Here's the dust cloud, and I've sort of drawn it such that all the blue light gets scattered in this example, and some of the half the red, yellow and green, and then mostly red gets through with a little bit of green and yellow. Okay. Here's my picture that I wanted to show you, taken from the International Space Station. Here's red light from the sunset that is just below the horizon, or sunrise. Can't really tell. And then the blue light because of particle scattering. Okay. And let's see. That's almost it. Almost it. So that gets us to the conclusions. Okay. We got to go back to the diagram real quick, which I had somewhere. Nope. It's before there. It's way back at the beginning. There we go. Okay. Yeah. Okay. So there it is. You see it? Blue light not getting to us. Red light not getting to us, but getting to us better than infrared light. And so shorter wavelengths, higher energy, more frequently scattered. Folks, we're dealing with dust. Well, what size dust? Let's zoom on through here real quick. And we'll get to the conclusions. Okay. Okay, the results, it depends. Okay, and this is where it gets complicated, but basically it could be any number of compositions. They don't know, there's no indication what it's made of, but if the dimming is caused by dust, it's going to range somewhere between 0.05 microns to 0.3 microns in diameter. Could you please say that in English? Sure. Virus-sized dust grains. Okay? And that's important because they're so small that radiation pressure from the star would have driven them away if they weren't recently produced. Okay? Dust must be recent. So there's something going on, right, around this star. Conclusions. Intrinsic variations, believe it or not, have not been ruled out yet. Okay? There are certain models that reproduce the light curves fairly closely with certain assumptions. Okay? I put this in yellow because, you know, some constraints, circumstellar material might cause secular dimming provided that the particles are bigger and that don't get driven away. Okay? Okay. Changes in the interstellar medium simply not detected, so it's not that. So we're eliminating things. Okay? Dust clouds associated with orbiting planetesimals not ruled out because we got to explain the dust somehow. Right? Exocomets could produce a lot of dust too, you know. A ringed planet, she didn't really address, the authors, the primary authors didn't really address this. I really kind of came up short trying to figure out if they had anything to say about it. I didn't see anything. Orbiting body, collisions, inconclusive but not ruled out because again, dust has to come from somewhere, right? Trojan Asteroids swarms, probably not, okay? And the reason I say that is because remember what we ruled out? Binary star system, can't be any Jupiter-like bodies or not very much bigger than Jupiter anyway, and so that kind of limits the number of Trojan asteroids that would be trapped in those special gravitational wells. And yeah, so we're kind of leaning away from that now. And like I said, I'm sorry folks, the headline said science fiction, the truth was more like science. But we can hold out hope.
Well, Dyson and dust.
Yeah,
right?
Sure they do.
There's a marketing thing there somewhere. Build a vacuum cleaner.
Yeah, but wouldn't a gargantuan mega Federation versus Klingon space battle produce a lot of dust? Huh? Maybe not the best hypothesis. Okay, so anyway. But this is how science works. This is what I wanted to kind of show you. We're not there. This is not the big reveal. You know, I can't tell you, and this paper nails it down, and that's the only thing it can possibly be. That's pretty rare. Pretty rare in science. But we're getting somewhere. Okay. Any questions? Yes?
Yeah, you may have said this earlier and I missed it, but what is the spectral classification of Kepler?
Geez, I knew I was going to forget to do that. It's an F3.
Okay.
Yeah, it's a hobbit star. I just really wanted to say this. You remember that before Bilbo and Frodo met Gandalf, they were respectable hobbits, right? They never did anything unexpected or went on adventures. How does that apply to an F3 star? An F3 star is a nice, sedate, well-behaved main sequence star. And Dr. Biagian said, well, you know, it's not a young star either. Okay, so it's settled down, right? It's not at the cutoff, or it's not at 0 ZAMS, if you know what that is. It's a nice, well-behaved star, and you know, and well-behaved stars don't pulsate, and they don't do all the things that other variable stars do. I was going to show you a graphic of the HR diagram, but those who have seen the talks on astronomy have seen that. It's a nice little stable region like the Shire. Yeah. Yes.
Well, until you just said that,
Okay.
it struck me that anytime you have transits or eclipsing binaries and things like that, you have very symmetrical dips.
Mm-hmm.
And all of the ones with jagged, unexplained, asymmetrical things are all intrinsic variables like Cepheus or RR Lyrae.
Mm-hmm. Okay. Okay.
Well, I guess if you want to call this a new kind of intrinsic variable where it's lots of trillions of tiny particles eclipsing, which is almost a part of the star itself, like in a cloud of dust.
Depends on how close, yeah.
It's if they rule out all these transit things as soon as you saw the first piece of data. I don't know why she spent so much time.
Like which data? You mean the
like
the dust
size and this size, ruling it out, and I mean you could rule it out just from looking at the one eclipse or whatever it was, one dip. It's not symmetrical.
Well, I think certainly planetary transits per se have been ruled out. What I didn't say about the Dyson sphere, the reason that's ruled out is because if it were an opaque structure, like a planet or an artificial construction, all colors would be extinguished at the same rate, and that's not what we see. Am I responding right? I don't know. Okay, and so that's why. So that was ruled out. The reason that some of these things are still in play is because these planets that we are not detecting with the dips. So whatever planets are carrying dust clouds along with them would be too small for transits to be detected.
There are some F-class variables, intrinsic variables, that are going back across, not main sequences.
Oh, okay.
Already been red giants and going back across. They go through an F region on the way down to the white dwarf or whatever they're going to do.
I'd have to look at that again. When I looked at the diagram I looked at, admittedly from Wikipedia, okay, the instability strip didn't seem to get that far. Yeah, because I think that's what you're referring to, the instability strip along in AGB regions and.
It's unstable. It's up higher.
Right.
It's not main sequence. It's brighter than that, but it's still F.
Right. I can't say this though. It's not at least currently behaving like a pulsator at all. Those light curves. That's not a pulsator, you know. So, but you know, who knows? Maybe some really weird, chaotic stuff happens that nobody's ever seen before at these margins. So, that hasn't been proposed. I don't know. Yeah. Yes.
So we're talking mainly about the star, right? Not about the planet?
We're talking about anything that it can explain these strange changes in the light output.
What about volcanoes on the planet?
It would have to be volcanoes. Yeah. Millions of them, I think. I don't know. I'd have to sit down and calculate to produce so much dust that it would, something really exotic. See what I mean? That's a good thought, but just like, and it's just as good as some of the others, you know. But it would require these strange, you know, like millions of them or something like that. I mean, kind of like the exocomets. Yeah, good thought.
Maybe another planet hitting it.
Like a volcanic planet hitting another one. Well, once two planets collide, you're going to get dust and molten material, and you know it's going to be
Hot dust.
a lot of hot dust, and it's going to go everywhere. And so yes, so I'm sorry, I'm in the back, sir. Yes, sir.
Thinking of this, and I mean, as far as the perfect scenario where it's going like that, I mean, that sounds good if you're talking about one planet crossing the sun. But I mean, if you're talking about multiple planets crossing the sun, and as they're crossing the sun, the planets are crossing themselves, isn't that going to create I mean, if the planets are moving at a different speed, isn't that going to create different amounts of light as you going across like that?
It could, but there would have to be, in order to equal the area of the 22% drop in light, you're talking about 1,000 Earths. Or maybe 100 gas giants or something. I don't know. It just staggers the, I mean, sure. I think that's where the exocomet idea was coming from, a swarm of these objects that are producing all this dust or something. But yeah. Oh, but
I mean, they don't have to be that big. I mean, it's in relation how big the planet is and how far away it's from the sun itself.
Sure.
I mean, if you depending on how close you are to the sun and how much further away, I mean, if the planet's closer to us than the sun, isn't it going to block more of the sun?
It will.
The size?
The reason that's being ruled out, though, is because the light, the different colors that you saw, those colors would all be together. It would extinguish as much if it were planets. If it were 45 Earths or 159 Uranuses, okay? Uranuses, there's no way to say that. Okay, 150 of those, and they were all coming by in a kind of a swarm of beautiful planets. Wow, I'd love to see that. Okay, they're coming by. It would block all colors the same amount. And that's what we don't see in the data. And that's why dust or some kind of star spot looks like, or exocomet, or the exocomets still look like they might be some of the best explanations.
Maybe aliens, maybe bacteria.
Yeah, ooh, it's their bacteria manufacturing, you know. Yeah.
All the dust in the universe was shed skin cells from aliens. He actually said that in this room.
Well, skin cells would be a little too big for this, but if they're skin cells as we know them, anyway. Yeah, yes, sir.
If it's circling the sun, shouldn't there be some regularity in the dips?
Yes. Yeah, you mean the dust? Yeah. If the dust clumps are moving, and there is some. Yeah, that's on the table. Good point. Because, okay, so there was some periodicity. Notice there was a repeated event in 2011 that was repeated in 2013. And they were looking for it to happen again in 2015. And there were no eyes on at that time. Nobody was looking. Yeah. So the 2017 dip might be the next one. So thank you. And now I get to make my plug. If you want to find out how to observe it, let me know. Cygnus is going to be rising in the east soon, all right, in the next couple of months.
Start looking.
Around midnight, by June. So yeah. That is being talked about. There just isn't enough data to rule either way. Yeah. Mm-hmm. Ooh, great questions. Okay. Anything else? Or?
Thank you very much.
Sure. Thank you.